For years, aviation followed one unbreakable rule. No fuel, no flight. Every aircraft ever built, no matter how advanced, has obeyed that law. Until one quiet test challenged it. Because what happened that day didn't look like a stunt. It didn't look rushed. And it didn't look accidental. Maxwell's self-powered aircraft didn't roar into the sky. It rose. Calmly. Steadily. Almost as if lift itself had been negotiated rather than forced. At first, most people didn't notice. The footage wasn't dramatic. No fire. No smoke. No aggressive acceleration. Just an aircraft leaving the ground without any visible sign of conventional energy input. And that subtlety is exactly why it was unsettling. Because real breakthroughs don't usually scream for attention. They whisper and let physics do the talking. Those watching closely began asking the same question. Not is it flying, but what is it not using? No fuel lines. No combustion signatures. No heavy onboard energy storage dominating the frame. Which meant the story wasn't about propulsion in the traditional sense. It was about how lift was being sustained. Engineers analyzing the flight noticed something strange almost immediately. There was no surge at takeoff. No spike in energy demand. The aircraft behaved as if it had already been airborne before leaving the ground. That detail mattered. Because in conventional aviation, takeoff is the most demanding moment. Everything is pushed to its limit. But here, the transition from ground to air looked smooth, continuous, almost indifferent to gravity. That observation forced a shift in perspective. What if the aircraft wasn't generating power on board? What if it was interacting with energy already present in its environment? That idea reframed the entire flight. The aircraft wasn't burning energy to overcome gravity. It was operating inside a structured energy field, one that allowed lift to exist without constant expenditure. And that's when the focus moved away from the aircraft itself, toward the space around it. Observers began noticing equipment positioned around the test area. Not traditional ground support. Not standard communications gear. But carefully arranged structures that suggested something else entirely, an engineered environment rather than a powered vehicle. This wasn't just a plane. It was a system. And once that realization set in, the flight stopped looking like a demonstration and started looking like a proof of concept. Once that idea took hold, everything people thought they understood about aircraft design started to feel outdated. Because for more than a century, aviation has been obsessed with one question. How do we carry enough energy to stay in the air? Bigger fuel tanks. More efficient engines. Lighter materials. But Maxwell's approach appeared to ask a completely different question. What if the energy doesn't need to be carried at all? That single shift changes everything. Instead of forcing lift through thrust, the aircraft seemed to synchronize with an external energy framework, one that already exists, but is usually ignored or considered unusable. The aircraft wasn't fighting the air. It was cooperating with it. This is why the flight didn't look dramatic. Drama comes from struggle. And this aircraft didn't look like it was struggling. Experts who reviewed the footage frame by frame noticed another detail that deepened the mystery. Control surfaces moved minimally. There was no aggressive correction, no constant adjustment to maintain stability. The aircraft behaved as if it were naturally balanced within an invisible structure holding it in place. That kind of stability isn't common even in advanced drones, which raised a new concern. If this wasn't brute force propulsion, then what exactly was being engineered? The answer, according to those studying the system, may lie in how electromagnetic fields interact with matter. Not as a power source in the conventional sense, but as a medium. A way to reduce effective weight, manipulate pressure gradients, and create lift without continuous energy burn. And that's where skepticism intensified. Because this isn't incremental innovation. It's architectural change. The kind that makes existing infrastructure obsolete rather than improved. If an aircraft can rely on field alignment instead of fuel, then airports change. Maintenance changes. Range limits disappear. And suddenly, the most expensive part of aviation, the energy, becomes almost irrelevant. But here's the part that unsettled observers the most. The test didn't look like a final product. It looked like an early version. No sleek design. No optimized aerodynamics. No attempt to impress. Which suggests the goal wasn't to show how good it could be, only to prove that it could work at all. And historically, that's how the most disruptive technologies appear first, not polished, not commercial, but undeniable. Because once something flies without fuel, even briefly, the argument is no longer philosophical. It becomes practical. From that moment on, the conversation stopped being about belief and started being about implications. Because even if the flight lasted only minutes, those minutes were enough to expose a crack in the foundation of modern aviation. A crack that can't be sealed by denial or dismissal. Think about what aviation is built on today. Global fuel supply chains. Strategic choke points. Energy dependency. Remove fuel from the equation, and you don't just change how planes fly, you change who controls the skies. That's why the reaction wasn't excitement. It was silence. No immediate endorsements. No major headlines. No rush to explain it away. History shows that when a technology threatens an entire ecosystem, it's often ignored first, not attacked. Silence buys time. Time to evaluate risk.
Time to decide who needs to respond.
Meanwhile, independent analysts kept looking. They noticed that the aircraft's mass-to-lift behavior didn't align with traditional aerodynamics. Its climb profile suggested reduced effective weight, not increased thrust. That distinction matters because increasing thrust requires energy. Reducing weight changes the problem entirely. If gravity can be partially neutralized rather than overcome, then flight becomes less about power and more about geometry. That idea isn't new. What's new is seeing it expressed in hardware. Which brings us back to Maxwell himself. He didn't present the aircraft as a miracle. He didn't frame it as a finished solution. He treated it like a natural extension of a principle he had been working on across multiple systems: energy generation, motion, and environmental interaction. To him, the aircraft wasn't the breakthrough. It was the evidence. Evidence that a broader framework works across domains. And that's the detail many people missed. This wasn't an isolated invention. It was part of a pattern. Generators that don't rely on fuel. Vehicles that appear to recharge themselves. And now, an aircraft that treats energy not as a consumable but as a condition. When you connect those dots, the flight stops looking like a fluke. It starts looking like a chapter. That question is simple, but deeply unsettling. If this framework works, why isn't it everywhere already? Because technologies don't spread based on possibility alone. They spread based on compatibility. And this one isn't compatible with how the world currently functions. Aviation isn't just planes in the sky. It's fuel contracts, geopolitical leverage, military logistics, regulatory structures, and decades of engineering doctrine. A system this dependent doesn't adapt quickly, it resists. Which explains why the most intense scrutiny didn't come from hobbyists or online critics. It came quietly from institutions trained to assess threats, not trends. Because a fuel-independent aircraft isn't just a commercial disruption. It's a strategic one. Imagine surveillance platforms that don't need refueling. Cargo aircraft unconstrained by range. Aerial systems whose endurance is measured in weeks, not hours. That changes defense planning at a fundamental level. And yet, despite all of this, Maxwell's flight wasn't presented as a military solution. There were no tactical claims. No performance benchmarks. No grand promises. Just a demonstration. That restraint is telling. It suggests confidence, not in immediate adoption, but in inevitability. When a principle works, it doesn't need to shout. It only needs time to be rediscovered by others. Still, unanswered questions remain. How scalable is the system? How dependent is it on external infrastructure? And most importantly, can it function outside a controlled test environment? Those questions haven't been publicly resolved. And that uncertainty is precisely why the story is far from over. Because breakthroughs don't announce their arrival. They reveal themselves slowly, through anomalies that refuse to disappear. That lingering anomaly keeps pulling people back, not because it promises easy answers, but because it refuses to fit inside old ones. Every attempt to explain the flight using conventional models runs into the same wall. The numbers don't collapse neatly. The assumptions don't hold. Something has to be bent, or abandoned, to make the equations behave. And that's usually the first sign that a system-level change is underway. What's especially interesting is what didn't happen after the flight. There was no immediate replication from major labs. No rushed prototypes from aerospace giants. Not even aggressive public debunking. Instead, there was observation, quiet monitoring, selective engagement, careful distance. That pattern appears again and again when a technology sits in an uncomfortable space, too functional to dismiss, too disruptive to embrace. Meanwhile, smaller groups began asking a different kind of question. Not, is it real, but what conditions made it possible? Because if the aircraft depended on a specific alignment, environmental, electromagnetic, structural, then the breakthrough wasn't just the machine. It was the configuration. And configurations can be learned. That realization may be the most consequential part of the story so far. If the principle doesn't belong to a single aircraft, a single inventor, or a single country, then it can't be contained forever. It becomes a matter of replication, not permission. Which brings us to where things stand now. The skies haven't filled with fuel-free aircraft. Aviation hasn't been rewritten overnight. Commercial flights still burn kerosene by the ton. But somewhere between what we see every day and what we're told is impossible, a different trajectory has quietly begun to form. One that doesn't rush. One that doesn't announce itself. And one that doesn't end with a single flight. Because once something has lifted into the air without obeying the rules don't snap back into place. And that is where the story truly pauses, not with a conclusion, but with a threshold. Because the question is no longer whether that aircraft flew.
It did.
The real question is what happens when the conditions that made it possible stop being rare. When understanding spreads faster than denial. When replication replaces speculation. Every revolution in aviation history followed the same pattern. First, disbelief. Then, dismissal. Then, quiet study. And finally, sudden inevitability. The Wright brothers were ignored. Jet engines were doubted. Stealth technology was once dismissed as fantasy. Not because they didn't work, but because they didn't fit the world that existed at the time. Maxwell's self-powered aircraft now sits at that same edge of history. Not as a finished answer, but as a disturbance in the narrative of what flight requires. If lift can be achieved without fuel, then energy stops being the limit. And when limits dissolve, timelines accelerate. So the skies remain unchanged for now. But the idea has already left the ground.